Good morning, everyone. I'm the technical host, and we're going to get started here. So I'll let the moderators take over, and excuse my, oops, sorry about that. I have a tech computer here running too, and forgot to turn the sound down on it. But we're ready to go.
All right, welcome everyone, and thank you, David, for getting this show started. First of all, thank you attendees and thank you sponsors for making the ABO 2020 Summit virtual this year and quite a success. Today, we will be having an industry spotlight that highlights maximizing carbon dioxide utilization for algae R&D. This panel will be co-hosted by myself and my colleague, Christy Sterner. I work for the Department of Energy and Fossil Energy, explicitly the Carbon Utilization Program. Christy, do you want to introduce yourself?
Sure. Thank you, Amishi. I am Christy Sterner, and I'm a technology manager for the Advanced Algal Systems Program in the Bioenergy Technologies Office for the Department of Energy. Welcome, everyone. Thank you.
So for today, the agenda will flow as is. Christy and I will actually open with a short presentation that's a kind of high-level deep dive of our respective programs. We hope to cover some R&D shaping documents, explicitly the NAS study on gaseous CO2 utilization. We'll also talk about how our programs help the R&D space and hopefully highlight projects that are taking that R&D and bringing it into industry. And finally, we will close out with really what the industry is doing in regards to carbon and LCA efforts. Christy will take it over now and give some technical details about the presentations and how things will.
Sure. So, as Amishi said, we'll start with a brief introduction before we jump into the first presentation. I just want to remind folks that there are two screens. I think you can open either the chat or the Q&A. So feel free to use the chat to say hi to fellow participants and to the panelists. And then we would ask that you put your questions into the Q&A box where they'll be saved and moved over to a screen where we'll be able to ask those at the end of the session. So if you do submit a question, you may not get an answer right away, and that's because we're saving those for the end of the session. People will be able to see them and you can interact, but we highly encourage you to use the chat for that. And then also I want to remind folks that you can go to the Whova app after the presentation, after the session is over, and continue dialogue with the panelists and with each other, and I highly encourage that. The Whova app is awesome and it's a great way to connect during the summit. So again, please enter your questions into the Q&A and we'll take care of those at the end of the session for anything you direct to our panelists. They will also be able to follow up with you after the session to answer more questions you may have and any that don't get answered during the session, and that can all be done through the Whova app. So thank you, and I will turn it back to Amishi, who will jump right into our introduction presentation.
Ooh. Let's see if I can get this to work. Oops. Sorry, guys.
So there you go. Got it.
There you go.
Fun fact about Christy and I, we work together, but we also don't like public speaking. I thought it was the worst, and then I was introduced to virtual public speaking, and it's gotten even better. Anyways, so I mentioned I am the Carbon Utilization Program Manager. So I work in fossil energy, and you guys are probably more familiar with Christy because she works in the Bioenergy Technology Office, which I know has been a workforce, especially in this algae industry. But I wanted to give a little bit more context of what fossil energy is doing in their carbon perspective when it comes to algae. So bear with me, it's going to be a little bit more carbon centric for the first slide or two. So starting here, the Carbon Utilization Program, right? It's in the CCUS division. So it's the Carbon Capture, Carbon Utilization, Carbon Storage Program. For a long time, for 2 decades really, carbon capture and carbon storage were, for 2 decades, having hundreds of millions of dollars, cumulatively billions of dollars invested into our economy and into the R&D space. So within the last 5 years, really, carbon utilization has started to gain more momentum. It started off with $3 million, then 10, then 12. And this last year is actually $21 million. And it kind of came from this paradigm shift on how we view carbon. So the carbon capture and storage linear pathway was capture that CO2 and then store it, put it underground, put it in EOR, enhanced oil recovery, store it in saline. But instead, we started realizing once you've captured it, rather than treating CO2 just like a waste material, it's actually an opportunity. You can do things. We can recycle that CO2 back into the economy, turn it into a valuable good. So with that came this program, and we've investigated a variety of utilization pathways. We have 48 active projects and another 11 on the way. And every year, I'm gonna jump to the left side and actually build up from those bullet points. Every year, Congress gives us investments explicitly in algae because they think it is a great space to be in, especially with this carbon use perspective. Just really quickly, I did want to touch down on the two other things that we investigate. We also investigate mineralization, so CO2 into inorganic materials. Hopefully what comes to mind is next generation concretes. We also investigate carbon conversion, which sounds like a vague blanket statement, because it is. It's pretty much you take CO2, a reactant, some energy, whatever shape, form, plasma, heat, electrons, and you turn it into either an organic compound of interest, like a fuel, a plastic precursor. And there's benefits to that. Obviously, it's a synthetic compound that has a large commodity market, but hopefully some of those words that I said kind of trigger, this algae perspective. It's really hard for us to make CC bonds or complex bonds in this conversion pathway. It takes a lot of energy. We do a lot of life cycle analysis, so figuring out if it makes sense to make a complex molecule. So while people in this electrocatalytic field have been, tirelessly working to get catalysts that can couple a carbon-carbon bond, the beauty of this biological uptake, this algae products, is that there's such a vast, suite of products that algae has been making. Our office really isn't invested in figuring out if the algae is, like a string or a floating bubble, or if it's red, or if it's blue, or if it's green. It's just a unit processing for us. But at the end of the day, algae is a technology that makes pigments and nutraceuticals and these things that we just could not dream of creating within the lab. So one defining part of the carbon utilization program is that we are interested in the whole breadth of products, but what we care for is to have a strong life cycle analysis of the products explicitly all the way down that life cycle chain, and having a techno-economic analysis if it makes viable sense. The other challenge that we have, and actually an opportunity within our program, is we have been through our work with CCS, the original sister programs. We have a very strong understanding of point sources of CO2. So that's industrial flue gases, that's coal power plants. So there are opportunities for these algal systems to integrate into the point sources and take advantage of whether it's waste heat or any other co-location benefits. So those are some broad perspectives that we have when we are addressing algal components within the program. And also we support whatever we can for as far as facilities for testing. We have actually an algae project going to the National Carbon Capture Center to test photobioreactors on a slipstream of flue gas from a coal power plant, which I think is a great way to show the intersection of our previous carbon capture and carbon utilization work and how that is actually helping algae. Now I'll turn it over to Christy because she's got a lot more algae to talk about. All right.
Perfect. Thanks, Anishi. And if you're familiar at all with the Advanced Algal Systems program within VITO, then you know that everything that Amishi was just talking about is very, very synergistic with what we do in the AAS program. So a lot of what Amishi led into is what we actually focus on. So we focus on the algae pathway from all the way from strain identification and strain development all the way through to product development. So there was a main focus on the entire pathway, and where it's super synergistic with the Fossil Energy Office and with what Amishi is working on is now we can take the carbon capture utilization technologies and processes that they're focused on and tie those in directly with algae cultivation and processing. So as you can see, it's a really good mechanism, good way for the two offices to work together synergistically and make sure, one, that we're not duplicating efforts, and two, that our efforts go together hand in hand and that we're capturing that CO2 and we're using it with an awesome organism out there with the algae that can make incredible products and really build and move this industry forward. So just briefly, as you can see, I mean, I love pictures. So there's lots of pictures of different types of algae cultivation systems and research and development going on this slide. That's what BETO does. We partner with the industry partners, with academia, and with the national labs to move the industry forward on the R&D scale. So as I mentioned, we look at everything from strain identification and development all the way through to products. Similar to what Amishi also said, we are very much focused on TEAs and LCAs, techno-economic analyses and life cycle analyses, because of course we want these technologies to work, we want them to be economical, and we want them to be competitive with the petroleum processes that are out there making the same types of products. So it's very important to have that TEA and LCA tied in there, reducing energy, water use, land use, nutrient additions and uses, all of those things to make them economical. It's really where BETO is focused. So next slide, please. Amishi also mentioned the many products that can be made from algae, and as folks on the phone know and the panelists, there are so many very cool products. The nice thing about algae is we can take it to an intermediate precursor for any number of amazing products. There are some pictures of some on this slide. There's also a couple slides or a couple pictures of larger, more pilot scale and commercial scale farms that are currently in operation. The main point of all of this is to let you know that BETO, the AAS program, we get between, I would say between $30 and $40 million a year to put into algae R&D. The biggest thing that we do is interact with industry. So my message always, whenever I do a presentation to all the wonderful folks that attend this, is to let you know we want to hear from you. We want to hear, what does the industry need? Where is the funding best spent? What is the next big arm of the R&D that needs to be looked at to help reduce those costs, get productivity levels up? And so, of course, you have a chance and you can interact with me, send me an email, send some Q&As, anything like that, reach out and talk to me. We're always happy to talk with you and hear what the industry has to say about how to move this forward. With that in mind, we put out funding opportunity announcements. Those are our competitive solicitations to fund projects in this area to help the industry. We have been doing this, so the algae program's been active again in our office since 2010. In 2015, we put out our first FOA that looked at both a direct air capture carbon utilization project as well as a flue gas. So we do both of those. And we have funded funding opportunities and projects in those areas since the 2015 FOA. In fact, if you're familiar at all with our FOAs that have gone out, we just closed our FY20 multi-topic FOA that was focused on kind of the whole food chain of algae. So it looks all the way from direct air capture and utilization of that CO2 all the way through to a product regime, including testing those products and their specs to make sure they meet industry standards. So as you can see by what's on the left, we're putting those out there. We want to hear back on if those are the right things to put out there and if the projects are what needs to be done in the industry to move forward. So with that funding spent and the FOAs that are going out, I think that the industry has made huge strides in being commercially successful, and we want to continue to do so. So I'll turn it back over to Amishi.
Christy did hit on quite a few of these. We did collaborate on understanding each other's FOAs. There's a lot of synergies that are now happening between our FOA topics, especially regarding direct air capture and how to increase carbon utilization within these. We work together to make sure our metrics speak to one another, we speak to one another. And as evidenced and will be evidenced throughout this panel, algae is in a really good space, in a really good position to make a carbon impact. And having a better understanding and a better literacy of LCAs, TEAs, or what we consider, or carbon technologies in general, carbon tech, would really help promote both the carbon tech side and the algae side. I mean, we say the algae industry is the early adopter of DAC. I would say it created DAC, let's be honest. But there are a lot of things that are pushing it beyond, you know, how it has been. 45Q is pretty much a production tax credit. That would be one way to frame it for carbon capture, utilization, and storage. They now incorporated with the latest tax update, in 2018, $35 for utilization with carbon, with algae species. And I think throughout the industrial spotlights, people have discussed the impacts of the Farm Bill and the policies pushed forth by USDA and the benefits it will have for the algae industry as well. I will let Christy, do you have anything you want to say about this one, or?
Well, just that I mean, we can use this to kick off into the first presentation. So as you can see on the slide, these are our speakers for the panel, and we are focused on the gaseous carbon waste streams utilization. So you'll see presentations that talk about the LCA associated with this, TEAs, and also the progress that's been made in the industry, the use of fossil slipstreams off our flue gas slipstreams for carbon utilization, as well as direct air capture. Lots of good stuff in these presentations, so glad you're all with us and hope you enjoy them. And if you want, Amishi, I can go ahead and kick off our first speaker.
That'd be lovely, thank you.
Sure. So our first speaker is Michael Burkhart. He is with the California Center for Algae Biotechnology at University of California, San Diego. And I would also point out too that he was also involved in this report, and we'll be sharing some of that with you. So Michael, turn it over to you.
Thanks for the opportunity to speak today, and it's my pleasure to discuss the work that I took part of in the study on gaseous carbon waste streams utilization. This was a study that was conducted by the National Academies. We started this study because it was commissioned by the National Academy of Sciences, by a number of government agencies, particularly in the Department of Energy, but also some large companies, particularly in the energy sector, with an interest in utilizing carbon that is being released as waste into the atmosphere, which is really happening all over the globe and certainly all over our country. We're really focusing on utilizing this carbon rather than sequestering it. There was actually a separate study done by the National Academies just focusing on sequestration. Here we wanted to turn carbon into useful and valuable products, things like fuels, building materials, plastics, and other types of chemicals, or animal feed or other type of foods. So our task was really to assess the status and progress of carbon utilization technologies, to identify the emerging technologies and analyze the factors associating with making them available at a commercial scale, to develop a set of criteria for utilizing this technology, to assess the major challenges, technical and otherwise, and the current research efforts, and finally to propose a comprehensive research agenda. The committee was made up of 12 of us from academics and industry. We were chaired by David Allen of University of Texas, and we were very ably assisted by staff from the National Academies over this 11-month study. We had some reviewers who came from industry, national laboratories, as well as some companies. And we gathered data over the course of 11 months. So not only did the committee members ourselves have knowledge and experience, but we also had 4 in-person meetings and 2 internet webinars back in the days when we could actually meet before COVID. We also looked at the literature and took community input through the website. In general, carbon dioxide waste is much more abundant than methane waste. So this is just showing in the year 2016, there were 5,000 megatons of carbon dioxide released as opposed to 26 megatons of methane. So there are many more opportunities to address carbon dioxide that's being made either in the power, industrial, transportation, or commercial sources. So we evaluated both carbon dioxide and methane waste gas utilization, although as I mentioned, carbon dioxide is more of a problem, and methane itself has energy affiliated with it, and so there are more incentives to capture that methane as opposed to carbon dioxide. And carbon dioxide has greater challenges in terms of discovering pathways to make it into a valuable product. Of course, both of these face challenges in terms of collection, capture, and purification. And CO2, because of its volume and the challenges in chemical dioxide. So carbon dioxide really has 3 major pathways that are used for its use. That's mineral carbonation, chemical conversion, and biological conversion. And enabling technologies and resources are really key to its utilization. And as I'll mention, LCA, life cycle assessment, and techno-economic analysis, TEA, are important evaluation tools. So in terms of utilization, as mentioned, there are really 3 pathways: mineral carbonization, chemical conversion, and biological conversion. These make these different products, either construction materials, chemicals, fuels, and other types of value-added products. Many of these have long-lived uses, but other ones, like the fuels, for instance, get consumed quite rapidly, creating their own source of carbon dioxide waste that can then potentially be factored back into this cyclic pathway. So these are the 3 utilization pathways. Mineral carbonization is really cement and concrete, and I spent a lot of time learning things that I didn't know about cement and concrete. There are tremendous opportunities for actually trying to capture the CO2 coming out of concrete manufacturing, which ends up being a very large portion of CO2 waste, and reincorporating that into products. But I'm not going to focus on that today. I'm also not going to focus on chemical conversion, although there are lots of opportunities. These are primarily in metal-mediated catalysis to make value-added products. Really, the point that I'm here is to discuss the biological conversion, and in particular, the green algae and cyanobacteria aspects of consumption of CO2 and applications. So we looked at a number of different types of products. What I'll say is that the majority of these products and their study are really all still in fundamental research when we actually think about the technological readiness levels. There's only a few technologies that have reached demonstration and or commercial application. Of course, biodiesel has already reached some limited implementation, and renewable fuels and renewable diesels as well. Animal feeds have reached some amount of demonstration scale, and probably the most successful of algae technologies are in the production of nutraceuticals, EPA and DHA among them being already sold on the market. And finally, of course, astaxanthin is a very nice source of pigment that is produced industrially by growing algae. The other area that's particularly interesting is the use of acetogens. This is primarily being done by the company Lanzatech, where these organisms can consume both carbon dioxide and carbon monoxide, and also hydrogen gas, and converting these waste products into valuable products like ethanol. In terms of the barriers, there's a number of key barriers that we identified. And we separated these into green algae, cyanobacteria, and then in general, chemolithotrophs and bioelectrochemical systems. In terms of algae, biodiesel is in and of itself a challenging product, and really there's not as much interest in biodiesel as there has been in the past, primarily because of the hygroscopicity and fouling products. Really all of the renewed interest is in renewable diesel and gasoline, and this is challenged by scalability, the ability to actually obtain the hydrogen, and having hydrogen that is potentially renewable is definitely a challenge. In protein production, really it's the ability to scale and the social acceptance of using this as an animal feed or potentially as human food. In terms of these existing products, really it has to do with growing that market because these products are already being produced. Cyanobacteria are a really exciting area of growth, and in particular, the ability to genetically engineer cyanobacteria is greatly accelerated when compared to green algae. So there have been a number of different really valuable and interesting commodity molecules that have been made by cyanobacteria. The challenge, of course, is the fact that these are really just demonstration in which really they suffer from low productivity in titers. And in general, the tools for genetic manipulation and scale up are just not there. Right, and that exists for all of these types of fine and commodity chemical products. Chemolithotrophs need a source of hydrogen, and actually fairly pure hydrogen, and scale up can be a challenge. And then in this area of bioelectrochemical systems, this is really in its infancy and has only been done on a demonstration level on the laboratory scale. In terms of a research agenda, we highlighted these particular areas. We need investment in the study of bioreactor and cultivation optimization, in particular carbon dioxide solvation, mass transfer, dewatering and harvesting, as well as recycling of water and nutrients. These are going to be very important as we start to take fundamental technologies and strain development and turn these into large-scale systems. We need improvements in analytical and monitoring tools just to monitor the cultures and in scaling them up to be able to make sure that production remains to scale. We need improvements in genomic tools, not only modeling and understanding metabolism and metabolic efficiency, but also tools for genetic manipulation, biochemical validation, and fermentative demonstration. All of these are going to be important for engineering the metabolism of these organisms for making molecules that will have value added to them and at a low enough cost that they can be actually made into products. We also need to improve our carbon dioxide uptake and incorporation, photosynthetic efficiency, metabolic streamlining, and product accumulation. Bioprospecting will always be important. We need to find organisms in the environment that have the improved activities and metabolites that we're interested in, and these can now serve as starting points for genetic manipulation. We're going to constantly need new co-products to be identified and valorized. because you can only, for example, produce so much astaxanthin until you saturate the market. So we need to find new co-products. We need to be able to convert these co-products to make molecules or other products that have value added that people are going to be willing to buy. Kind of as was mentioned before, we need improved genetic tools. We're still a long way away from meeting parity with, for example, yeast or E. coli in terms of our ability to genetically engineer and optimize pathways, and these are going to continue to be important. And finally, pathways to new products to be able to produce either non-traditional products or new. Methane, as I said, I'm not going to focus on this, but of course there are both chemical and biological conversion methodologies for this. In terms of biological conversion, there are methanotrophs. Some of these are being implemented on the demonstration scale, and in this case, where methane can actually be converted into things like ethanol through methanotropic conversion. We also really wanted to focus on the importance of life cycle assessment. This is really the only way to compare technologies to each other and valorize them so that we can then implement them in the marketplace. We identified factors that can be used to assess the commercial viability, and the first, of course, is economic value, right? Do we actually have products that have some value added to them? The scale, market capacity, and market penetration. Really, how big is this market, and how could we penetrate the existing market with these types of carbon recycling? Well, we missed the end, but I was pretty much at the end of the presentation.
We hope, though, that what we propose is going to.
Perhaps David can get it going again.
The recording dropped there. You want me to start it from that point?
That's fine.
Okay. About at 2 minutes. Give me just a second here. Stand by.
So everything that we said, really, these are going to be weighed by different people, and it's going to be very different to different people in different sectors. We hope, though, that what we propose is going to be taken seriously, particularly by government. Of greenhouse gas emissions, and the U.S. government really should follow this. Development of enabling technologies that will help facilitate the ability for these technologies to be implemented. Our second recommendation is to coordinate with existing efforts. So, there's already efforts underway, and we really need to strengthen and support them in order for us to see a real change within our lifetimes. So, a final thought. We really need all of the tools that are available to us, not only the mineral, but also the chemical and the biological systems to deal with this. We need an all solutions rather than just one solution in order to really meet the challenge that lies ahead for the problem of waste carbon. So finally, thank you all for your attention. I encourage you to download the report online. It is free. at this website. And I think that there's lots of opportunities for us to use this as a tool to convince our funding agencies that this is an area that really needs concerted and applied attention. Thank you very much for your attention.
Well, thank you so much for that keynote, Michael. It was fantastic, and it was a really good overview of what we're going to be tackling and what our programs actually tackle. Christy mentioned how much we rely on industry and input from you all in the attendees to help shape that R&D agenda, and that document is a fantastic example. Now we'll transition, and we will be getting a presentation from Michelle Krynock. She works at the National Energy Technology Laboratory, so NETL. And for those that aren't aware, NETL supports fossil energy in their program execution. So they are the people, when I say LCA, they are the ones that are helping assess LCA across the entire carbon utilization portfolio. And just one note, I know we're having technical difficulties. Things are getting a little jittery. I'm assuming it's because we have so many people from all over the world. So if anything cuts out, please just try to log back in. We will keep going through it. So I think with that, Michelle, you should be up next.
Quick disclaimer, I'm a KeyLogic Systems Inc. contractor with NETL. I don't work directly for the government. So I want to start with a brief overview.
My apologies. We are having a few technical
Although it's
difficulties
simple,
that you mentioned. I'm going to back up on this presentation.
So I want to start with a brief overview of what is LCA. LCA is a method of looking at the entire life cycle of a product or technology. So you look at cradle to grave, from raw material acquisition all the way to final disposal, and add up all the environmental impacts in between. Although it's simple, you can actually use it for a lot of different things. So we can establish national baselines, so looking at the entire nation's methods of producing said product or technology to get a single average for the country. Or you can regionalize or get more interesting with that. But you can also narrow down and look at a single technology and emerging or existing and just assess that and look at, all of the contributions along the way. You can take that a step further and then compare it to other technologies or the same technology under different scenarios. So different regions, different time periods, maybe different setups within the technology, different efficiencies and things like that, to look at how they compare environmentally. And then you can take that even further and plan for the future. So you can look at what certain decisions or changes in technology may do in the future environmentally. We frequently mix and match these techniques, so it's very common to take a national baseline and compare it to other specific technologies and scenarios, and things like that. The goal for this presentation is to give you a sense of why all of these are important and just how interesting and complex these things can be based on what question you're asking. So for my first example, we're looking at an algae LCA that we did more recently. This is based on the NREL studies, the NREL farm study and NREL PBR studies, as well as some additional information. We take their sort of TEA technology setups and turn them into complete LCAs. This diagram gives you an overview of all of the different technology pathways we include, but it can essentially be simplified down to this. So we're looking at multiple CO2 sources, multiple cultivation methods, dewatering methods, and conversion methods. So we're taking all of those scenarios, coming up with an environmental impact for them, and then also comparing them to petroleum, diesel, and business as usual co-products. So for the duration of this, I'm going to assume that this audience has some background on the algae aspects of this, so ORP and PBR and those sorts of abbreviations. If you don't understand them, you can always chat me with questions. So the main focus of this study is to look at these scenario trade-offs. So holding all things equal, what's the difference between an ORP scenario versus PBR scenario, HTL versus CAP, and flue gas versus captured gas. Our first example, this open raceway pond versus photobioreactor. Our first example, this open raceway pond versus photobioreactor. Based on holding everything else equal and just changing the cultivation method, we found in this instance 7 percentage point reduction going from PBR to ORP. So on the global warming potential scale. The x-axis of that graph is fairly important. That's percent of the comparison case. So petroleum diesel baseline plus business as usual, other co-products, ethanol, animal feed, things like that. So it makes it a little bit complicated, but because different pathways make different sets of co-products, you can't directly compare them. You have to compare their performance against their comparison. So we found that flue gas sort of came out on top environmentally. This is primarily because of the electricity required or the energy required to capture CO2. Another major caveat here is that we were looking at power plant upstreams from previous NETL studies. So our flue gases specifically are pretty impure, like 10 to 20% CO2, and our captured CO2, the capture system, is powered by the power plant itself, these fossil fuel power plants. So change those things and you might see a different gap size. For example, if you could find a flue gas stream that's more pure and therefore getting the benefit of more efficient algae growth, that gap would probably widen. But as CO2 capture technology gets more efficient, that gap will shorten and things like that. But this is what we found based on our assumptions. So hopefully that gives a pretty good overview of just how in-depth and complex these things can get. Just on this one LCA we did, we were able to tell that yes, these are generally more environmentally preferable to the business as usual cases that we were comparing them to. But more than that, we were able to look at what each scenario, how each scenario performed and compare them to each other. And we were also able to look at sort of hotspots. So looking at the environmental contributions, for example, the PBR environmental impacts, very sensitive to electricity usage and profile. So if you're doing PBR, you might want to look more at using renewable energy and things like that, or just lowering your usage in total. And of course, the process of doing this really opens up what data is needed. So these are obviously low TRL, and these things are expected to change over time, but just the process of going through it can tell us where more data is needed. Our next example is a completely different question. So this is the CO2 LCA guidance toolkit. This is something that we created to help PIs, DOE funding recipients, to create their own LCAs of their own CO2U projects. So we have a guidance document that makes sort of a simplified LCA process and all of these tools to help them walk through each one. One of the major pieces of it is that OpenLCA LCI database. OpenLCA is an LCA software that can do your LCA calculations and also hold all your data. So we created a database that has existing environmental profiles for PIs to be able to use in their own projects. But we also created an example complete project. So for the example, we used an algae pathway. This is what it looks like in the software. But it's essentially fairly similar in scope to the other one. But there are some main differences. So because this is an example for the PIs, this project focused on one question. So does this project perform better or worse environmentally than what I may be taking into the market in the future when I commercialize? So what we're calling marginal cost technologies. So one of the major differences between these studies is we're comparing it to two different things. And this is largely because it's a lower technology readiness level. There's some uncertainty about what they'll be facing in the future. And it will be a little bit dependent on costs and things. So we want the PIs to take a closer look at that and what the consequences are of them commercializing. So not only that, but we're doing less about all of these different scenarios. We're assuming that the PIs aren't looking at ORP and PBR at the same time. We're more focused on just the variability within that pathway. So looking at, what if we manage to increase efficiency or decrease electricity use and stuff like that. And so we're not looking at Monte Carlo because these are meant to be simplified LCAs, but we are looking at high and low uncertainty and sort of the breadth of possibility within this pathway. And because this was done earlier than the NREL studies were available, we used an example literature source. So the results are not meant to be definitive and representative of those people's work. It's just an example. But yeah, from there, we hope that PIs will be able to take that information and help form their own and answer those questions in the same way. And so they can use LCA to look at those questions and those possibilities. So hopefully this has been enough to convince you that LCA can be used in a variety of ways to look at all kinds of different questions. And even looking at the same technology, you can look at it from different angles, and LCA can give you all sorts of important information depending on how you're looking at it. Thank you very much.
Awesome. Thank you, Michelle. So that was a really good presentation on LCA and how it's being looked at and done. I highly encourage folks to reach out to Michelle if you have questions or just want to generally talk to her about LCA for your particular system and technology. And with that, we will move on to our next speaker, who is Bruce Rittman. He is with the SVET Center for Environmental Biotechnology at Biodesign Institute. And I think I saw him on here. Are you there, Bruce? You are up next. Here we go.
Good morning. I'm happy to tell you today about highly efficient CO2 delivery from industrial sources. I'm Bruce Rittman from Arizona State University. First, let's talk a little bit about industrial sources of concentrated CO2. First of all, there are many of them, and this table shows you the wide range of them, and by looking at this, you can see that they're everywhere. But what's doubly important here is that the typical concentration of CO2 in these gases ranges widely, from as low as 5% in a natural gas power plant to up to 100% in fermentation. So any system that is going to be delivering this kind of industrial CO2 needs to be able to handle the wide range of CO2 concentrations. Now, CO2 delivery is very important for macroalgae cultivation. First of all, microalgae need a lot of CO2. Carbon is more than 50% of their ash-free dry weight, plus we use CO2 to control the pH. Now, not only is CO2 important, but efficient CO2 delivery is essential. The cost of CO2 is around $90 per ton of dry biomass if the CO2 is provided with at least 90% transfer efficiency. But sparging, commonly used today, has transfer efficiency less than 30%, making the CO2 cost greater than $270 per dry ton. This is becoming far too high. In addition, if we're trying to remove or capture CO2 from a fossil source, we can't be losing 2/3 or more of the CO2 to the atmosphere. So for all of these reasons, we must have CO2 delivery efficiency that's approaching 100%. So how are we going to get this? Membrane carbonation is the approach we're working on. Membrane carbonation, also I'll be calling it MC for short. So MC is a way to provide carbon dioxide with about 100% delivery efficiency, precise pH control, and minimal marginal cost. MC is an adaptation of the technology, the membrane biofilm reactor, that my team has been working on for more than 20 years. In the membrane biofilm reactor, we're delivering a gaseous substrate like hydrogen to a biofilm that's removing pollutants from water. In MC, we're not removing pollutants from water, but we're delivering CO2 to grow microalgae. So how does MC work? This schematic shows the basics of the system. So in the center of the graphic, you'll see in green the microalgae cultivation. And you'll see in there hollow fiber membranes that are suspended. Now, one side of the hollow fiber membranes is connected up to the CO2 source. It can be a wide range of CO2 concentrations. Also in the culture is a pH probe connected to a pH controller. And this pH controller turns on the CO2 supply valve when the pH goes above a set point. For example, let's say we set the pH at 8.0. If the pH just goes above 8.0, the CO2 supply valve is open, so CO2 is delivered to the membranes. Now, what's very important in MC in this application is what's happening on the other side of the membrane, the distal end. Now, when you're operating with gases that are not 100% CO2, the CO2 is selectively removed into the medium for photosynthesis, and the other gases, the so-called inert gases, accumulate. Now, if you let this go on too long, soon you don't have any CO2 and you don't have much CO2 transfer capacity. So what we need to do is periodically sweep out the accumulated inert gases. And we do that at the distal end using the venting valve. It can be either controlled by the pH, where we have a second set point a little bit higher that opens the valve, or we can use what we call a bleed valve, which is a very small, steady flow of going out the distal end. Now, we have a project to develop the strategies with MC. It's funded by BETO. It's called Membrane Carbonation for 100% efficient delivery of industrial CO2 gases. And the goal of it is to develop the strategies to manage the MC system so we can achieve nearly 100% carbon transfer efficiency for the range of CO2 sources. And in particular, we're ranging from 10% to 100% CO2. Now, we have a special focus on digester biogas. It's about 35% CO2. And here we get a double benefit. On the one hand, we're delivering CO2 to grow the microalgae. And on the other hand, we are removing CO2 and concentrating the methane in the gas so that we can produce what we call biomethane, our natural gas line quality methane. And this is of tremendous economic value to the utility. All the work is being done at ASU. The lab work and the modeling work is being done in my center in the Biodesign Institute, and the outdoor work is being done at the Arizona Center for Algae Technology and Innovation. Now, I want to point out that we have a great cooperation with the city of Mesa, which has anaerobic digesters in their wastewater treatment, and with the Salt River Project electric utility with power plants. So the project has a wide range of tasks that we're doing. I only have time to tell you about a couple of them, and one of them is the bench scale testing we're doing with Synodismus acutus. And we're using our two-valve system. I talked about it before. There's a little diagram to remind you. And here the goal is to manage the distal end so that we get simultaneously a high CO2 transfer efficiency, approaching 100%, and a high CO2 flux so that we can deliver the CO2 fast to the microalgae. Now, we've done a lot of experiments, so I can only present a little bit of it. The overarching conclusion is that we can obtain stable pH and biomass productivity with CO2 from 10% to 100%. And we're getting promising results. So here's one set of results that illustrate what I'm saying. So here we're showing some results for going from 10% to 50% to 10% CO2 in the feed. Let's take a look at the 50% CO2 case in the upper right-hand corner. In red, in the top panel, you can see the pH. And when the light is on, you can see the pH is varying between 8, the set point, and a little bit below, about 7.85 here. In the panel below, you can see traces of the valves being turned on. The blue one is the turn on of the supply valve, and the orange one is the turn on of the venting valve. And you can't really see it, but I can tell you that the supply valve is on about 40% of the time here, and the venting valve on 25 or 30% of the time. Now, if you look at the bottom set, you can see this is for 10% CO2. You notice the valves are on a lot. They're really on a lot. With 10% CO2, you've got to be sweeping out the inert gases frequently. But the system works quite fine. And in fact, you can see from the red lines that we get really precise pH control with these lower CO2 contents. Now, this graph is very important. The blue bars show us the biomass productivity, and the orange bars show us the amount of CO2 that goes into inorganic carbon. And this is for the range of experiments with the range of CO2 content using MC from 100% down to 10%. And we also did sparging in parallel. The important thing to see from these bars is that they're all the same. Our goal was to have the same productivity, the same pH, and so these bars should have been the same, and they are the same. So we achieved the same productivity performance in all systems, no matter the CO2 concentration. What's really more interesting are the red triangles. These are the carbon utilization efficiencies. And so if you look at the far right ones, you can see the red triangle for sparging is at about 20% CUE. That translates to about 25% carbon transfer efficiency. Typical, not so good. If you go to the far left, for 100% CO2, we never have to open the vent valve. We get 80% carbon utilization efficiency, and we get 100% carbon transfer efficiency. Perfect. Now, some of the triangles in the intermediate ones are pretty low. However, the one that's really important and promising is the one for 100% bleed. And there you can see we had a 60% carbon utilization efficiency, 73% carbon transfer efficiency, which we consider to be really good at this very small scale in the lab. It's very hard to precisely control the flows and turn the valve on and off fast enough with this small scale. We consider this promising, and we know we can do better at larger scale. So how about larger scale? So here are pictures of our raceways that we've been doing outdoors at Ascati. So the right-hand picture is the actual 400-liter raceway in action. The far left picture is one of the membrane modules that you can see we made for this. You can see it's a woven fiber between two manifolds. And you can see in the middle picture, we placed just one of these manifolds into the raceway near the bottom of the raceway, and it provides all the CO2 that we need. So we ran these systems, 3 in parallel. One had sparging with CO2, and 2 had membrane carbonation of CO2 using our MC system. So here are the results from one of those tests. Let's look first at the bottom graph. This is the productivity, the biomass productivity. We ran these three systems, two MCs, one sparging. We ran them in parallel. We tried to get the same conditions and the same productivity, and we did. We have the same productivity for all of them. It varies, from day to day, but it's the same. What's really important is in this middle graph. And in the middle graph, you see how much carbon dioxide we had to deliver to get the same productivity. And you'll see that the CO2 delivery for MC, that's the squares, is about threefold lower than we had to deliver for sparging in the triangles. And in fact, our CTE in this larger scale system with MC was around 100%. So we achieved it very well here outside in Reefwise. So with this, I'm coming to end my talk. I hope I've convinced you that CO2 delivery from industrial sources is a good and important idea. Second, that highly efficient CO2 delivery is essential. And third, that membrane carbonation is the way to achieve all of that. Thank you very much.
Thank you, Bruce. That was awesome. I learned so much from that presentation, so I appreciate that. Up next, we'll have Jason Quinn, Dr. Jason Quinn. He's an associate professor at the Colorado State University, and he will be touching down on the economic and the life cycle potential of microalgae-based bioplastics, something that we're all very interested in. And we'll try to get that presentation up. And as a reminder, guys, please submit your questions into that Q&A. We really appreciate it. We hope to have a very active Q&A session afterwards. And if we don't, probably wake up at 2 a.m. wondering where we went wrong. So please put in that Q&A.
Hello, I'm Jason Quinn. On behalf of all my co-authors, I'm excited to be here to present our work on the sustainability of the production of fuels and bioplastics from microalgae. As I get started, I first want to acknowledge and thank the Department of Energy for financial support for this work, and then partners at Algix, University of Kentucky, as well as Colorado State University. This is an overview of the talk that I'm going to give. First, going to give some background behind the work, overview how we did the work, and then the primary results from the work. As we look to algae products, we're really looking for high value, high market size. This is the target. In reality, what we've seen in the literature is it ranges anywhere from huge market size and low values, specifically fuels, animal feeds, to very low market sizes but very high values such as nutraceuticals. With the bioplastics area, we're really targeting this area. So it's kind of in the middle of the market size and in the middle of the value. So let's overview the work that we're doing and how we're doing the work. So specifically, we've got 4 unit processes that we're looking at, and I'll go into detail on each one of these unit process operations. The growth system, we've looked at 3 different growth architectures. One is a photobioreactor system illustrated here on the left. So this is what's being done at University of Kentucky. It represents a very low energy system. There's the standard open raceway pond system that's illustrated here on the right. And then our third architecture involves a hybrid system that includes both of these growth architecture systems. Biomass is dewatered through a 2-step process. First, a low energy settling tank, followed by a vacuum filter belt. The vacuum filter belt results in approximately a 20% solid paste, which moves on to downstream processing. The downstream processing, there are 3 different pathways that we look at. One that represents just drying the biomass, and then 2 that include a bioplastic feedstock as well as a fuels production. The fuels production is generated in 2 different pathways. One is a fractionization process that's being pioneered out of NREL, and the other one represents a simple lipid extraction, which has been demonstrated at University of Kentucky. When we look at the fuels pathways, the biomass has 3 parts: protein, lipids, and carbohydrates. And so depending on the pathway, you're targeting different fractions of the biomass. So the fractionation process, fuels are being generated from the lipids as well as the carbohydrates, and the bioplastic feedstock is limited to the protein fraction. With the lipid extraction pathway, you just are targeting lipids, and the protein and the carbohydrate are going to bioplastics. In terms of producing a bioplastic feedstock, this is the entire process needed to generate the bioplastics. Our system stops at the point at which the feedstock is generated prior to the plastic production. So this includes further dewatering and drying, and then preparation such that it can be seamlessly integrated into the plastic process through milling. So pulling everything together, these are the various pathways that we've modeled. So in the green are our different production pathways. We have a fixed dewater system. And then in the yellow are different conversion pathways. As I mentioned, there's 3 different conversion pathways: drying of the biomass for a pure bioplastic feedstock, and then the lipid extraction and fractionation pathways that enables us to produce 2 products, fuels, as well as a bioplastic feedstock. So in total, we've got 12 different pathways that we can go through, including the 3 different cultivation systems, as well as the 3 different conversion pathways. So let's go into some of the detailed methods on how we do some of the sustainability work. So specifically working with our partners on the experimental side of things, University of Kentucky for the cultivation and conversion side of things, and then Algix for the characterization of the biomass in terms of a bioplastic feedstock. At Colorado State, we were doing all the system modeling work as well as evaluation, and the evaluation through sustainability included technoeconomics based on BETO and plant assumptions, which I'll go into more details, and then for the life cycle side of things, leveraging OpenLCA coupled with the EcoInvent database, which again, I'll go into more details on. The technoeconomic analysis is a 30-year discounted cash flow rate of return analysis. The primary inputs are based on the engineering process model and include capital costing as well as operational cost, as well as the performance of the system, specifically bioplastic feedstock production and fuels production, if applicable. What we do is we use standard assumptions such as an internal rate of return of 10% and loan financing, depreciation, etc., to calculate the required selling price for the bioplastic feedstock, such that at the end of the 30-year life, we have a net present value of 0. For the life cycle assessment, we are leveraging the engineering process model to capture the required energy and materials that go into the system, and then coupling that with life cycle inventory data out of EcoInvent primarily, but supplemented with US LCI and GREET. The environmental impact is quantified through a global warming potential, the metric specifically being the CO2 equivalence. That CO2 equivalence includes 3 primary gases, which are CO2, methane, and N2O, using the IPCC 100-year global warming equivalency factors of 28 and 298 respectively for methane and N2O. So let's go into the results. So one of the things that I'd like to point out is that this facility is primarily a bioplastic feedstock production system. So on the vertical axis is the total production on a per hour basis out of our system. As you can see, for the 2 fuels production pathways, there's very minimal fuels being produced compared to bioplastic feedstock. And so I want to reiterate, this is a bioplastic feedstock production facility with a co-product of fuels. With that being said, so looking at the results, this represents an ORP growth structure combined with our 3 different downstream processing options. The vertical axis has the minimum selling price for the bioplastic feedstock in dollars per kilogram. So as we look at this, there's some important things to point out. First of all, capital cost dominates, similar to other studies have shown, and this capital cost is rooted in the cultivation platform. On the two conversion pathways, I'll note that there's co-product credits. These co-product credits are specifically for the fuels. So lipid extraction has a lower fuel production, thus a lower co-product credit, and the fractionation has a higher fuels production, hence the higher co-product credit. When you pull all of this together, again, so on the vertical axis, we're looking at this minimum selling price required. On the horizontal, we have our three different growth architectures combined with the three different conversion pathways. The orange dotted lines represent the current bioplastic market, or what the selling prices can be depending on the quality. The gray bars represent the totals. So some things to highlight here. The open raceway pond really represents the most promising. As you integrate photobioreactors into the growth architecture, it represents a huge capital cost and dramatically increases the minimum selling price for the bioplastic feedstock. That being said, one of the things that is not included here and represents future work is understanding the reliability increase associated with integrating photobioreactors into your growth systems. So looking at life cycle results, so similar to what I presented before, this represents an open raceway pond growth architecture and then the three different processing pathways. The totals are presented here in gray. So a couple of things to highlight. Specifically, that you've got this CO2 credit that is associated with the carbon uptake in the biomass. We're assuming that the bioplastics are long-lived bioplastics, and the carbon that go in there represent sequestered carbon from the atmosphere. Another thing to note is that you've got credits associated with the two fuels conversion pathways, but you also have combustion associated with those fuels that are contributing to the total global warming potential that's being determined. Similar to the TEA, the LCA results, we've got a summary graph here. The dotted line represents the current environmental impact associated with plastics. The three growth architectures across the bottom, and then the corresponding three conversion pathways. What you'll notice here is across all of the pathways, we see very promising results from a life cycle perspective, drastically lower than current plastics. So in conclusion, what we've done here is we've determined the minimum selling product price, specifically that algae bioplastics have the potential to be commercially viable as a feedstock based on current markets. We've also looked at the emissions for the system, as I just presented, is that all of the pathways represent environmentally promising pathways. And then lastly is that the fuel production doesn't necessarily represent a good choice. When you look at the drying only pathway, because the value of the bioplastic feedstock exceeds that of the fuels, currently that represents the most promising pathway for the production of an economically viable as well as environmentally friendly bioplastic feedstock. I thank you for your time and I hope you have a wonderful day.
Awesome. Thank you, Dr. Quinn. That was a great presentation on bioplastics, and you know, it's kind of become a really big deal. Not kind of, it has become a big deal and a big area of interest within the industry and also within VITO. So I'm really glad to see that presentation and drum up some additional questions and interest in that. I also really appreciate the TEA and LCA incorporation into the project and how you're looking at alongside the research. It really shows how those are both incorporated right in there. I would want to remind folks, please send those questions. We're looking forward to a really active discussion after the final presentation. And then to do my lead in for the final presentation, I'd like to introduce David Hazelbeck, who is the CEO of Global Algae Innovations, and he will be our final presenter. When his presentation is done, we will come online all live and you'll have a chance to talk directly with our panelists and ask them questions, get their answers to the things that you've submitted, and then of course follow up with them on the Whova app. So with that, I will turn it over to Dave.
Hi, I'm Dave Hazelbeck, CEO of Global Algae Innovations. Thank you for the opportunity to participate in this important discussion. In this presentation, we will look at algae solutions to global dilemmas and focus on three in particular: carbon dioxide mitigation, deforestation, and the water-food energy nexus. But before we jump into these, hi, I'm Dave Hazelbeck. The title of this talk is also the purpose of our company, Algae Solutions to Global Dilemmas. Our vision is to harness the unparalleled productivity of algae to provide food and fuel for the world, dramatically improving the environment, economy, and quality of life for all people. Global Algae Innovations was founded 6.5 years ago, and because our target is global impact, we are looking at algae for commodities, feed, food, fuel, and polymers. Our goals could not be achieved by incremental changes or even a couple of breakthroughs in the algae production process. We need order of magnitude reduction in costs and even more in energy use. So to date, all of our focus has been research and development on radical advances throughout the entire process to achieve these very challenging cost and energy use targets. This past year, we achieved the final breakthroughs needed to project economic viability for commodities. So now we are working on a 20 times scale up from our current 8-acre farm to a 160-acre farm. This is an aerial photograph of our algae R&D farm. As I just mentioned, there are about 8 acres of open raceways, and the largest is a little over 3 acres. Initially, we developed and implemented a carbon dioxide capture and delivery system that provided flue gas carbon dioxide for about $20 a ton. We operated using that system for the first 5 years, taking a slipstream of flue gas from the adjacent power plant to provide the carbon dioxide needed for algae cultivation. In the past year, we've developed a direct air capture system where we capture carbon dioxide directly from the atmosphere. This system is less expensive and untethers algae from fixed carbon dioxide sources. So we've moved to this method as our primary approach for carbon dioxide supply for R&D at the farm. Algae is the solution to so many global dilemmas because it offers unprecedented gains in productivity for agriculture. Looking at the chart, the y-axis is protein yield in metric tons per hectare per year, and the x-axis is oil yield in gallons of gasoline equivalent per acre per year. All conventional and non-conventional crops fall in the lower left quadrant, with modest oil productivity and very low protein yield. The demonstrated productivity for algae, illustrated by the green points, is in a totally different realm from other crops. And algae is a nascent industry, so we're just getting started on things like breeding and other techniques. So the potential of algae is even greater, as illustrated by the red point in the upper right-hand quadrant. For perspective, the green revolution in agriculture, fertilizer, pesticides, GMO crops, intensive farming techniques that saved the world from starvation in the last 50 years was a 2.3-fold improvement in yield. Algae offers a 40-fold improvement in protein productivity and a 5-fold improvement in oil productivity, with the potential for even greater yields. The impact of this level of productivity is amazing. So for the rest of this presentation, we will look at 3 of them: climate, deforestation, and water. We'll start with carbon dioxide mitigation. In order for algae production to happen worldwide, we need direct air capture to remove the tether to fossil carbon dioxide. This plot provides a comparison of cultivation using our direct air capture system to cultivation with flue gas carbon dioxide added. The y-axis is productivity in grams per meter square per day, and the x-axis is time in days. The raceway with direct air capture achieves the same productivity as the control where flue gas carbon dioxide is added. This illustrates that large-scale algae facilities no longer need to be located adjacent to carbon dioxide sources. Algae production is essential to meeting our climate change goals. Producing a large fraction of our animal feed and biofuel from algae would mitigate about 13 gigatons of carbon dioxide per year. For animal feed, algae achieves a 60% reduction in greenhouse gas emissions. So producing 32% of our agricultural output for protein from algae would mitigate about a gigaton of carbon dioxide. The co-product oil produced with this protein would provide about 200 billion gallons of fuel per year, or about 20% of the global demand. Algae achieves a 94% reduction in greenhouse gas emissions for fuel, so this would mitigate another 2 gigatons. Even larger CO2 mitigation comes from using algae protein for animal feed and vegetable oil because it will stop and reverse deforestation. Almost every IPCC scenario to achieve our climate change goals relies on stopping and reversing deforestation. Until now, there was no practical way to achieve this outcome. Algae feed production provides the path to actually achieve the goal of stopping and reversing deforestation, and thus algae is indispensable if we are to achieve our climate change goals. The reductions noted are based on life cycle analysis of global algae's cultivation systems. Several references are also included to peer-reviewed papers that have come to the same conclusion. Algae for animal feed is pivotal in achieving our climate change goals. Let's look at 2 land use examples. Protein production is the primary cause of deforestation in the Amazon, either for soy or for ranching that has been displaced from non-rainforest land by soy. Over 100 million hectares of the Amazon have been lost. But income from this protein production is very important. So despite major efforts to slow the rate of deforestation, it's actually been increasing in recent years. Building 400 algae farms could solve this problem, enabling restoration of all of the Amazon rainforest while producing more protein, generating more income, and creating high-quality jobs for Brazil and other South American countries. This is possible because algae is so much more productive than other crops. The chart illustrates the land required to produce protein from different sources. The units are meters squared of land required to produce 1 kilogram of protein. What becomes immediately obvious is that algae is in a whole different order of magnitude from other plants and animals. And this is why building algae farms could lead to the restoration of the entire Amazon rainforest. In Southeast Asia, palm oil is the primary cause of deforestation. Palm oil is the most commonly produced oil in the world because it has the highest productivity and lowest cost. As a result, over 18 million hectares have been deforested. Demand is expected to quadruple, so rainforest destruction in Southeast Asia will quickly become on par with destruction of the Amazon. On the other hand, palm plantations have been important in eradicating poverty and enabling education, so there's no easy answer to slow this deforestation. The chart illustrates that palm oil is 5 times more productive than other land plants for vegetable oil. However, algae is 25 times more productive than other land plants and 5 times more productive than palm, so algae could be the solution. How could algae be used to restore the rainforest in Southeast Asia? Oil palms have a limited lifespan of about 25 years before they need to be replanted. Since much of the boom in oil palm began earlier this century, these plantations will begin to need to be replanted in the next 5 or 6 years. If algae were installed to replace palm plantations as they reach their lifespan, we could restore the rainforest over the next 25 years through the natural cycle of palm plantation replacement. Algae would provide more vegetable oil to meet the growing demand and generate more income. Algae farms would also create high-quality rural jobs, so as the populace becomes more educated, they have local high-paying jobs. And since high-quality protein meal would be produced along with the oil, the protein meal could be used to support a large sustainable aquaculture industry, further improving the local economies. Aquaculture is already a major industry in Southeast Asia, and FAO estimates the demand for aquaculture is going to triple. So this is an ideal use of the protein co-product. Finally, let's look at water use. Agriculture accounts for 70% of our water withdrawals, and agricultural runoff is a leading cause of global water impairment. As illustrated, water use by crops goes primarily to transpiration to keep the plants cool. plus a substantial amount of water is lost via percolation into the soil and runoff. Evaporation from algae raceways is typically about 30% higher than transpiration, but algae farms have no losses from percolation or runoff. As a result, the water use per acre for crops and algae is similar. However, algae produce 40 times more protein per acre than other crops, so algae farms use 93% less water for protein production. What does this water savings mean in a practical sense? Let's look at the Colorado River as an example. The historical flow in the river is about 5 trillion gallons of water per year. Of this flow, 4.2 trillion gallons is diverted for agriculture, primarily alfalfa and hay, and the rest is used by industry and households. As a result, the Colorado River did not reach the sea from 1998 until 2014, and now a small amount reaches through purchases of water rights, but it is a tiny fraction of the historical flow. If we build just 8 commercial-scale algae farms to replace alfalfa, then we could leave 2 trillion gallons per year of water in the Colorado River while generating more income, the same amount of protein feed, and freeing up 2 million acres of land. This gives you some idea how transformative algae will be in restoring watersheds and wetlands. In summary, the scale-up for algae commodities is starting, and it needs to happen quickly because algae is the solution for many global dilemmas. Lastly, I'd like to thank the U.S. Department of Defense and especially the U.S. Department of Energy and the BETO algae team for supporting this technology development. Of course, all of the thoughts and conclusions in this presentation are global algaes and should not be interpreted as official positions or policies of the U.S. government. Thank you.
Thank you so much, Dave. That was fantastic. Overall, the panel has been great. We have been able to grow from academic to a very global perspective on many different aspects, LCA, water impacts, global impacts of environmental impacts. So it's been fantastic, and obviously that carbon story has been throughout the entire presentations. I also want to take this moment to say thank you to the AVO staff and all the people that are working working really hard behind the scenes. Megan and Megan, Barb, Val, David, and also Nate. They are working really hard to get the Q&A up and running for us. So now we will transition to the Q&A, and please, if you guys start getting more questions, put them into that Q&A option and we will get to it. And if not, it will be addressed via the Whova app afterwards. So Christy, I think I'll read the first one and see how that one's going. Oh, the first one is us. The question reads, isn't the capacity for carbon capture by algae very small compared to the power plant emissions, especially considering land availability, diurnal cycles, and seasonal variability of algae cultivation productivity? I don't know. I think I might have connection issues. No, I'm kidding. That's a really good question. Yo, do you want to take it first and then I'll follow you, or do you want me to tackle it, Christy?
I'm actually trying to pull it up, so.
Okay, well, I'll go for it first because I think this ties really well into some of the questions that we have to tackle all the time, right? So one coal power plant would inundate the market of the top 10 carbon utilization products that you could make, especially like C1, C2 compounds. So you're right, coal power plants especially produce way more carbon that could be consumed either in a commercial conversion pathway, like an electrochemical pathway, and also in a biologically mediated pathway. With that being said, there are great benefits beyond the carbon, right? You have wastewater benefits, you have energy efficiencies. What you also are getting is when you do a life cycle assessment, you need to also consider the offsets, right? From the algae, you're not just storing it, you're offsetting a conventional fossil-based product. So when you do a consequential or a complete LCA even, you will be incorporating, now you're having a bio-based plastic rather than consuming a fossil fuel-based plastic. So sometimes those carbon impacts that you're seeing aren't just from the storage capabilities, but for producing different kinds of products. So it's higher, but you are correct. The CO2 produced from these point sources is huge. So having a tool set, whether it's geologic storage, whether it's mitigation efficiencies, or algae-based bioproducts, they all work in cohesion, and you need every single one to make a real carbon impacts. Christy, do you want to add anything up to that?
Sure. I think what I would just add to it is that, of course, it opens up the opportunity if you can do co-location, and you can maybe even pull just a slipstream off of there for an algae farm, depending on the location and the size and the things you can do, that it opens up the opportunities for a true biorefinery, right? You can add in this algae farm idea and co-locating and pulling that slipstream off, because you're right. I mean, the stuff coming out there, there's so much more than an algae system would likely use or need, but that doesn't mean it couldn't work out. There are trade-offs all along the way. So maybe you open up your product regime for that particular plant in that particular area. Plus, there are so many synergies with the plant, things that you can use, waste heat and waste products, wastewater, things like that. You can also use the algae system on some remediation type things for your plant area, and then feed the products from that back into your plant. So there are definitely some positives about co-locating, despite the sizes and the usages and the actual capture from that plant. But on the flip side of that, I would also say this question leads directly into why would we look at direct air capture, and what are the benefits of direct air capture, getting away from co-location, being able to use the air directly instead of trying to pull these slipstreams from these very large sources where maybe capturing the flue gas could be used for something else on a much larger scale. So I think that the research and development is very necessary, looking at both, but cases can obviously be made for both just based on what this question is getting at by itself.
Very good question, though. Christy, you want to tackle the next one or read off the next one?
Sure.
Thanks.
So our next question is for Dr. Rittman, and it is the algae consumption of CO2 the limiting factor, or the absorption of CO2 at a fast enough rate into the water? At a fast enough rate into water. So again, I'll repeat that. Is the algae consumption of CO2 the limiting factor, or the absorption of CO2 at a fast enough rate into the water?
Yes. Okay, if we design the system well, then it will be the rate of photosynthesis that is rate limiting. So we set the delivery capacity from the membranes to be greater than the photosynthetic rate, and then the photosynthetic rate will determine it. So we should never be limited by the ability to deliver CO2.
Great, thank you.
Okay. All right. The next question is actually to Michelle. How long does carbon have to be sequestered in a product? How long does it have to have? How long does carbon have to be sequestered in a product for the utilization to be considered meaningful?
Yeah, that's a very good question, and there are some philosophical aspects to that, of course, about what is meaningful. I want to start with this. The analysis we did does not have sequestration. It's more of a cycling thing. So we are assuming that the fuels get burned, so the CO2 is not sequestered in the algae or algae product. So that being said, it can still be meaningful because we're avoiding the other CO2 emissions. So we're considering that we're displacing petroleum products, and we're preventing the CO2 from the power plant from being emitted immediately. So it can still be meaningful, but it is not considered sequestration. For the guidance document for PIs, I think we put in like 100-year cutoff point, mostly for logistical reasons. If you can prove that it'll be sequestered for 100 years, we won't question the end of life for that. But it's very philosophical, since CO2 is in the air forever. Theoretically, you want it to be sequestered forever. But yeah, it's kind of a arbitrary cutoff point.
Thank you. That was fantastic.
Okay, so I'm kind of bouncing back and forth here, but our next questions go to Dr. Rittman. There's some questions about what is the membrane made of, and does it have enzymes immobilized?
Yes. Okay. So the membranes that we normally use are made out of polypropylene. It's a one-layer membrane, 200, 250 micrometers in diameter. These are very inexpensive and also very durable. So that's why we use them in this application. And no, they don't need any enzymes or anything like that attached to them.
Wonderful, thank you. I would probably throw in there, just to combine it really quick with some of these others, like what is the lifetime of the MC system? Is it days or weeks?
Yeah, well, okay, so I'm going to answer that question in two parts. So first of all, we've adapted the gas delivery system from the membrane biofilm reactor. And this is a system we have tested for many years. And the systems operate continuously for years without any problems. So we know in these other applications that the membranes themselves and the system itself is very durable for a long time. MC is new, so we haven't had the opportunity to test it for those long durations. But in the laboratory, we've run the MC system for many months continuously without problems. The MC application is a little tougher because you're out in the sun and the elements, and so it will be more demanding. But we anticipate that you won't be replacing these membranes on a frequent basis.
Wonderful. Thank you.
Actually, I think we have, to build off that, your questions, Bruce, does any biofilm form on the membrane modules?
Good question. So in the MC application, the answer is no. Now, as I mentioned, we've been working with the membrane biofilm reactor for decades. And of course, we want to form a biofilm on that. But the MC application is totally different. And so the microorganisms stay suspended. And we've, of course, operated this for a long time in the lab and outside, and we've never seen any problems with biofilms. My explanation is you're delivering CO2 and the pH right at the membrane is really low. This is not where the microorganisms want to be. So they're suspended normally, and we're just pulling the CO2 through due to the sink from photosynthesis.
That's great. Little co-benefit, I like that. I think I can tackle the next question, Christy, and then we'll go back to our alternating. This one, I believe, is for Michelle. And the question is, what if the photobioreactors used solar power, pardon. I know you kind of hit on in your presentation the benefits of when it would be really tangible to use renewable power and stuff. So if you want to elaborate a little bit more here.
Yeah. Obviously, if the photobioreactors are using solar power on site, that would lower their greenhouse gas emissions. You do want to be realistic about planning for co-locating with a power plant and also bringing in your own solar power. That's why we didn't assume that, but it's definitely like a scenario you can look into. It would lower the GHGs. You can also do a break-even analysis to understand, how much renewable power you would need to purchase or use to break even with what you're comparing to, if you wanted. There are a lot of different scenarios you can bring that in, just outside the scope for this one.
That's perfect.
Thank you, Michelle. So now we're going to go back to Dr. Rittman. We have another question for you. And I'm sorry, this one's kind of long, so I'll try and read it all at once so that you can understand what they're asking. When growing algae from certain waste CO2 streams, like cement protection plants, the algae often become laden with toxic heavy metals, which reduces their use in downstream applications. For example, they cannot be used for animal or human feedstocks. What can be done with the algae other than use it as a carbon capture sequestration stream?
Wow, that's a pretty broad question here. I would have started at the beginning on that. And So for cement kilns or coal-fired power plants, there are lots of other things in the gas and that could be harmful. But it's only harmful if it gets in contact with the microalgae. And so one of the aspects that we are looking at with the MC system is the degree to which using the membranes prevents the contact of those materials with the organisms. A lot of them are actually in very small aerosols, and they're never going to get through the membrane. And the other ones might get through, but they're not going to get through unless they're really pulled through by some metabolic action. And so we don't know this for all of them. It's one of our research tools, but we actually think that many of them will not actually make it to the microalgae, which would render this a moot point. Now, if they do get through and they get in with the algae, then this will change things. But I'm not the expert to answer that question, so I think I'll just not try to answer something about which I don't know much.
I like that. Good answer. Yep.
I will take it over. I will say that we have a couple projects in the fossil energy portfolio that are actually looking at that exact issue on impacts to animal feed. Obviously, nitrogen, phosphorus actually are micronutrients, so that isn't so much a deal. But once you are looking at heavy contaminants like mercury, the narrative changes quite a bit, right? So that's a very good question. We'll actually transition the next question to Dr. Quinn. Very nice work, by the way. Why did you focus on long-lived bioplastics versus single-use? Is there more value to the long-lived bioplastics?
Yeah, so I think this is, and I saw another question in the chat as well that's kind of related to this in general, right? And this, Michelle touched on some of this as well as in terms of, do you want a biodegradable plastic or not, right? And I think it depends on what your ultimate goal is, because a biodegradable plastic re-releases CO2 back into the atmosphere, whereas one that does not is a sequestering of CO2, right? And so I think that in kind of picking up on some of the stuff that Michelle talked about, and this is one of the challenges with life cycle assessment, is that it's really important that there be ethical practitioners out there that we're making the right assumptions. So integrating a solar farm, for example, is that really a good assumption? Is that practical? Because it's skewing results one way on the life cycle, but not on the economic, and then negative on the economics. And so in a roundabout way of answering the question directly is that, we were working directly with Algix, and Algix is the one that was giving us values for the biomass that was being generated and the different constituents of those. And so they're the ones that were really kind of the bioplastic leader as a part of that industrial project. So thanks for the question.
Thanks, Dr. Quinn. So actually, there were a couple questions related to that, and I will open it up to the next one that actually follows right on to what you're talking about. And it's basically, it looks like the bioplastics can be cost competitive. Do the bioplastics have any performance limitations, whether real or only perceived, which hinder their acceptance into general commodity use?
Yes, that's a great question. And, Algix was working directly to understand the performance and then the corresponding value of the plastics that are being generated from the different conversion technologies that we were investigating. And so when you look at the bioplastics in terms of whether they're going to be accepted, right? I mean, I look at this equivalent to the organic movement, right? Is that, there was a huge, or, another great movement was the high protein yogurt, for example, is that what people are going to adopt and why they adopt them is a huge unknown sometimes. And that represents something that, if all of a sudden now we're moving towards green chemicals, bioplastics, that can really resonate with community members that are hitting on the organic movement, for example. And so we're starting to get into the willingness to pay aspect of things. And, but I will say, when you've got huge industry people like Nike investigating these things, it represents a huge opportunity, because you just never know what that market might look like as it kind of, what consumer desires want and need. So I hope that answers the question in a roundabout way. I know that the specific question was on bioplastic performance, and Algix, in doing their work, was seeing similar performance to other bioplastics that they were generating based on the biomass that University of Kentucky was providing to them for the experimental work.
Perfect. Thank you.
That was actually great. That that got me thinking, and this question actually is going to be directed to Dr. Burkhart. First, thanks for your keynote. It was really good. I know that NAS study was incredibly hard. It was a heavy lift. Thank you for getting it done. And kind of what Jason was talking about, these societal pressures, these drivers, whether, you had a lot of people, I guess, coming to the table with their own perspective and their own issues. Did those drivers, did those perspectives, those desires, I guess, shape this research agenda, or what you guys kind of prioritized as your key summary points? Or did you not take into consideration this adoption, like this drive for biodegradable plastics or other things that are happening in the algae industry?
Sure, thanks for the question. I think just as preface, in my presentation, I'm sure that a lot of people at this meeting already knew a lot of the things I already talked about. I think what's really important was to communicate this to the broader country, to the government and to the people who are making decisions. And so, I hope people saw this as an opportunity to kind of communicate our message. But we heard from a lot of people. One of them, for example, was Dave Hazelbeck, who came and gave a great talk to the committee. But we also heard some kind of wacky stuff from people who were, creating their own carbon sequestration facility in their backyards. So there was a very broad mix of information and opinions. Really, our job was to distill this down to what was real science, and where we could actually place numbers where things actually had LCAs and TEAs conducted on them, and how we could actually logically compare all of these disparate technologies to each other, right? It's very hard to compare, growing algae biomass to, a cement factory, and how these have differential carbon inputs and outputs. One thing that I think was a really important take home was how we are going to need to kind of fit technology to the different sources of the CO2. So, for instance, as was discussed in this in the talks, coming off of a flue gas, you could have anywhere from 5% CO2 to say 20% CO2, and that you would have to purify that CO2 in order for it to be used, say, for a metal-mediated catalytic method, right? You cannot use these kind of dirty forms of CO2 in catalysis. However, algae like it just fine as long as you can absorb the carbon dioxide into the medium. There was also a question about things like heavy metals and other types of contaminants. And of course, the purification of any of these methods has to be kind of plugged into the LCA. But it was really interesting how there's tremendous cost in actually purifying, compressing, and transporting carbon dioxide. And for me, the best take-home message was this discussion of co-location, of how can we co-locate energy production, water purification, and algae biomass growth in areas together. And those are questions that really, those types of decisions are rarely made by the same groups of people. So we need a lot of people listening and working off of these ideas.
Thank you. That was really good. Appreciate that. Christy, do you want to tackle the next question, or do you want? Oh, you're on mute.
I keep doing that. Sorry about that. I am on mute. So actually, I think I was going to jump down with that good lead in and ask Dave a couple of questions that have popped up here. One of them came in and said, can you elucidate more on the principle of direct air capture of CO2 devices?
Sure. So, and I'll also actually touch back maybe on the couple on co-location as well.
Please do.
Because that was really what we focused on for the first 5 years, really, of our operations. But for direct air for all CO2 capture, the one thing I want to emphasize, the cost is not just the capture, it's also delivery of the CO2 to the system. And if you have thousands of acres of raceway, that can actually be substantial and even more than the cost of actually capturing the CO2. And so you really have to think of it as an integrated system. You have to tie it into your techno-economic analysis throughout the whole process. So you're really only looking at technologies that are both, that fit within the economics. For the direct air capture, we're looking at capture right at the raceways, basically. We've developed different engineering and different design of systems, basically, that allow us to capture at the raceways. For the flue gas, we're capturing in an absorber, as you noticed may have noticed on the aerial photograph. And then the CO2 was actually supplied with the water supply to the raceways. So there's no independent distribution. In terms of, one of the questions was how much could you actually capture and do the scales match in terms of land availability and other things near point sources. We had done a study about, I don't know, maybe 3 years ago where we looked at just power plant, cement, and a few other major sources. We didn't actually look at biogas or in some of the other ones, fermentation, but just looking at those major ones, we found that there was enough land near those point sources that would be, and in climate and other things that would be useful for algae growth, that you could actually capture about 800 million metric tons, which, as was pointed out, that's not the whole thing. That's a part of the solution to carbon capture and sequestration, but it's still a significant amount of carbon, and it generates 400 million metric tons of product, which is a significant amount of product. I think, in terms of feeds, that gets on order of the level of feed produced in the world. It's definitely on order or maybe even larger than the amount of polymers produced in the world. So we certainly could capture a lot of carbon dioxide in the US just looking at those sources. And then finally, tying to some of the other ones that Bruce mentioned, I just want to make sure people caught that in his presentation. One of the important applications that we've seen is when you capture CO2 with algae, you typically are pulling just the carbon dioxide and a few other things, sulfates and other things out of the gas. That's a great use for cleaning up biogas, so that then you can go a long way toward putting the methane back into the gas system. And so if you wanted to, so algae is an ideal technology to co-locate for cleaning up biogases to make them more valuable to be able to put back into the gas distribution network.
That was fantastic. Thank you so much. Good drawing from other people's presentations too. I appreciate that. We are getting a little bit, like the last 10 minutes, maybe the last couple questions, but I do still want everyone to encourage, please continue putting in your Q&As. They will be addressed. People are consolidating them, and we will follow through on the Whova app. So let's squeeze in just one more question if we can right now. This one is actually towards Michael, Christy, and me. Is there a global discussion on the mitigation / reutilization of CO2 that could impulse the legislation's countries towards the use of this kind of technology? So I guess on that global arena, are people really pushing legislation? And I would say there's a lot of technical push and policy push, right? With clean energy ministerial, on these ministerial level perspectives, utilization is now becoming a top contender, especially I'm coming at it from the CCS world, right? The carbon capture and storage side. Utilization is now brought up into every single meeting, the viable option. It's what people are investing in. Japan is doubling down on their efforts. Germany, the UK, and I think one reason is whether it's algal, whether it's commercial, like electrocatalytic conversion, it's just great to view CO2 not just as a waste, but as a product. And the algae industry has been doing it for by far one of the the longest periods of time and has been doing it very well. Christine, Michael, do you guys have anything you'd like to add in?
Rishi, that was a great answer, and you're a very good public speaker. Yeah, there are a number of countries. I would say it's very individualized right now. You know, Australia, Japan, the EU. It seems like everyone is kind of doing this independently. One would hope that maybe the Paris Climate Accords would be a good opportunity to organize these types of things, but obviously we're not part of that. So right now it seems kind of dispersed, but you know, hopefully as we start to generate some policies here, we can work with other countries. But right now I don't see a lot of collaboration.
So I don't have a lot to add to that. I think those are both great answers. What I would like to do is maybe open up that question more globally to the rest of the panel, because I know the other folks on the panel as well have lots of interactions with folks internationally as well as with congressional parties and things like that to help with legislation and actually push these types of things forward. And I think it fits really well in with not only the analysis that was done under this report, but then of course the LCAs and TEAs that are done on the individual projects. And it also feeds right into Dave's presentation about looking at the water issues and the deforestation and all of those kinds of things. So I would throw this out to the rest of the panel and say, what are your thoughts on this, about legislation and pushing this forward, not just in our country, but other countries, and addressing these issues that have been pointed out in the report? Somebody want to jump in? Jason, maybe?
Sure, I'll start. I think that we're doing a lot of work in, carbon account, integrating TA and LCA, right? To do carbon accounting, to do carbon, a lot of people hear it as social costing of carbon, right? And globally, this is something that's resonating in terms of what that looks like and how that gets deployed. The EPA, for example, has a structure right now that's in place. And understanding the impact of those policies is important. So right now, the EPA policy, due to the time value of money, makes it so the later you adapt, the better off you are. And so that's counterintuitive. And so if you look at more globally, social costs of carbons and what they look like in integrated assessment models, early adoption is better. And I think the real message I'm trying to convey here is there's a huge opportunity to integrate life cycle assessment with technoeconomics. Usually they are run independent and they're not talking together. Especially when you integrate temporal resolution with emissions and integrating that into the already temporally resolved technoeconomic modeling work. There's a lot of impact, and I think the point there is that it can change answers. It can dictate technology requirements, for example, in order to meet certain economic targets considering environmental impacts. And so, my global perspective is that let's start integrating these two, evaluating the impacts of policy and ensuring that they're going in the right direction. So that's kind of my high level perspective on that.
Great, thank you. How about you, Dave?
So I would say, first of all, we haven't really been trying to push the benefits of algae utilization because of the TEA aspects, as Jason just kind of referred to. We wanted to make sure that algae really could hit the economic targets for commodities, because even the higher value ones that we pointed out at plastics, it's still $2 a kilogram. Algae nutraceuticals are $20 to $30 a kilogram. That's a big gap. And so we have not wanted to generate too much enthusiasm until we felt we could get there. And so this is really actually one of the first public presentations we've made, presenting some of our data on what the impact could be in terms of deforestation and water, because we didn't want to generate a lot of excitement. The solution was still so far off. Now that we're close, now that we're starting to scale, we are actually going to try and start working with groups. I think algae is so unknown, though. We need to focus really on other nonprofit organizations like World Wildlife Fund, like some of the rainforest groups, other groups, to try and create a groundswell to realize algae really is a solution, and they can help magnify the message, because I think we're too small of a community kind of right now in terms of the number of people that know about it, and we need to really expand that now that, and I think the timing's right. And if you look at where we are, where a few other companies are, we're looking to scale to pilot. We might And let's say we have that within the next 2 years. That means in 2 to 3 years from now, we'll be ready for commercial scale plants. That's about the right amount of time to start to try and get this out through the other organizations so we can create a more of a groundswell when we're ready to really roll out commercial facilities.
Wonderful. Thank you. So I'm sorry to cut all of this off, but we are at the end of our session, and I would love to hear more comments from the rest of the panel. I would also like to thank all of our presenters, our panelists, our behind-the-scenes folks that made all of this work. And I know there were some minor technical issues, but they were on top of it like they always are. I'd also like to thank the organizers. Of course, the summit is awesome and encourage you all to continue participating through October. And then I would like to encourage folks to get together on the Whova app, continue this discussion, and also we will be submitting all the rest of the questions to the panelists so that they can answer your questions offline out of this session and hopefully get together with you on the Whova app. So from myself and Amishi, if you want to jump in and add to that, thank you. And thanks for a great session.
Thank you so much. Just one thing. Please consider attending the next industrial spotlight. It's macroalgae biomass and a sustainable feedstock for food, feed, fuels, and chemicals. So thanks again, guys. Appreciate it.
Good.
Yeah, big round of applause. Woo-hoo! Thanks, everyone.
Thank you.
Bye.
Bye.